Now, as the exam date is approaching, probably I'm getting lots of questions about my office hours. Well, whenever you can find me, ask me questions. I mean, I try to put office hours, but then there are other last-minute meetings, and I have to cancel the office hours. You come to my office hours. I'm not there. I don't like it, so just whenever you can find me, ask questions.
It's in the third floor.
Fourth floor. If you cannot find me in my office, or if you are, I don't know, coming from a long distance that you don't want to come here and knock on my door and not find me, send me an email the day before, probably, then we can fix a time. Sure. I speak Turkish. I mean, you can also ask questions in Turkish. Other questions now about the material? Where did I lose you? Okay, let's do this example and you tell me what to do. Now this time I will imagine not a wire, but an infinite cylinder. It goes up to infinity on both directions. And I will say that the charge density, now it's not a linear charge density, but if you just imagine any volume inside, well, I will assume that it's not uniform. Let's say you take a very small volume, delta V, at some point R, and then you calculate the total charge within that volume. And the charge per unit volume is, let's call it sigma. But it changes from, as a function of your distance from the center of the wire. It's not uniform. For example, if this is a conducting wire, sigma will be 0 everywhere inside, but it will be non-zero in a very thin region on the surface. That will be for a conductor. Or if it's uniformly charged, then sigma will just be a constant. But the important property of sigma is that it should depend only on the distance from the center. It shouldn't depend on whether you are here or here. It shouldn't depend on the z coordinate. It shouldn't depend on where you are, or if you just cross, it shouldn't depend on the phi angle, only on the distance from the center of the wire. Now, and I would like to find the electric field let's say at a point inside the wire. This is the radius of the wire. And I just pick up some point inside the wire. Let's say this point, P. What is the electric field at that point? Now, the steps are always the same in applying the Gauss law. First, you need to know something about the electric field. You need to know where the magnitude is constant, in which direction it is pointing at different points. That is the first thing you always have to determine. And then, based on that knowledge, you need to determine a surface over which you can evaluate the integral of the electric field. Either the integral is 0, or the integral, you can take the magnitude out of the integral, and you can so evaluate the remaining integral. So that's the criteria to choose your surface. And then once you determine the surface, the rest is just basically integration and using the Gauss equality. Okay, so how do we proceed first? What can you say about the electric field? Constant where? Everywhere. So the electric field is always pointing upward or downward. Perpendicular to the surface. Which surface? Okay, so here it will be perpendicular, upward. Here it will be in that direction. Here it will be in that direction. So the electric field, the direction of the electric field, that direction we call the rho hat. Also, don't get confused. Rho, we also use the symbol rho for the charge, volume charge density before. This rho is the distance from the z-axis. This is my z-axis. Rho is the distance from the z-axis. You can also write it as square root of x squared plus y squared. If this is the z-axis, just choose this is the x, this is the y, for example, and rho will be just the square root of x squared plus y squared. So, okay, one thing we know about the electric field, it is always in the away from my cylinder, away from the central axis. What about the magnitude? What can you say about the magnitude? First of all, can the magnitude depend on phi? Why not? Yeah, the charge density doesn't depend on phi. If I rotate my cylinder around the center, nothing changes. When I look outside, if I rotate it, nothing changes. But if I rotate it, I'm basically changing the phi coordinate of various points. So nothing should depend on the phi coordinate. Can it depend on z? We say that it cannot depend on phi. Can it depend on z? No, because the charge density doesn't depend on z. If I just push it along its axis, the charge density doesn't change. So the electric field magnitude should also not change. So that tells me that it cannot depend on z. So the magnitude of the electric field depends only on the distance from the center. Just like in the previous case. Whether this is an infinitely thin wire or, as in this case, it's a thick wire, it doesn't make any difference as long as you know that the charge density depends only on the radial distance. You see, if charge density depends on z, for example, if charge density told me that at this point there is a very large charge which doesn't appear anywhere else, but if this is a special point where there is a large charge accumulation, if I push the wire, well, that point will move over here. It will not be the same anymore. That would tell me that the electric field magnitude should depend on z. The electric field at this point will be different than the electric field at this point, mainly because at this point is closer to the accumulated charge, whereas this point is further from the accumulated charge. So there will be a z dependence in that case. But in this case, there's no such accumulation over there. Or if the charge density was such that I have very few charge on the bottom and very large charge on the top, well, if I rotate it, it will look completely different. So if that were the case, the electric field would have depended on phi also. But since this is not such a case, the electric field depends only on rho. If the other cases were true, like we had a charge accumulation in a region, or we had a very large charge on the top, very small charge on the bottom, for example, then since we couldn't find a simple form for the electric field, okay, Gauss's law would still be correct, but it will be just useless. We will not be able to use the Gauss law to determine the electric field. But in the given case, we can. Okay, so now we know the electric field. We know something about the electric field. We know that it is pointing away from the wire, always perpendicular to the surface. And also it depends only on the distance from the central axis of the wire. And now we have to choose a suitable Gauss surface. But you see, this is just exactly the same problem as the previous infinitely thin wire case. The surface over which the magnitude is constant is just a cylinder. So we take a cylinder and close the cylinder by two flat surfaces whose area vector is perpendicular to rho hat. Well, I'm looking for a point inside the cylinder, so I will just assume my Gauss surface is also inside the cylinder. I will just imagine such a Gauss surface. The evaluation of the Gauss integral for this surface will be exactly like before. There won't be any change. Again, we divide the surface into the flat parts plus the curved side, E dot dA over flat sides, plus E dot dA over the curved surface, well, over the flat sides, the electric field is perpendicular to dA, so this will give me 0, this scalar product. On the curved surface, the electric field E and dA, they are pointing in the same direction. But now, over the curved surface, rho is constant. I can just take it out. Now this dA is nothing but the total area of the curved side, which we had said was just 2 pi rho times L. The height of the cylinder is L, and the radius of the cylinder is rho. From the previous part, nothing has changed from the previous example. If it was an infinitely thin wire, I would have chosen the same Gauss surface. I would have evaluated E dot dA in the exactly the same manner, and I would get exactly the same result. That is what we did before. Or if I had chosen a Gaussian surface which was not in the wire but outside the wire, exactly the same derivation. This result that the E dot dA is equal to E times rho, 2 pi rho times L doesn't depend on whether my Gauss surface is inside or outside. I will have exactly the same result. Now let's look at what happens, how we use the Gauss law. Well, Gauss law tells me that this integral is equal to the total enclosed charge divided by epsilon 0. Now, what is the total enclosed charge? In the previous case, we just said, okay, we knew the linear charge density, we knew the charge per unit length. We multiplied that charge per unit length by the total length, and we obtained the total charge inside. But here it will not work that way, because the charge is not uniform. So we have to determine, well, let me just plot it over here again. This is my cylinder. This is the central axis of the cylinder. The enclosed charge. Now, if the charge density were constant, it would have been easy. Just multiply the charge density by the volume. But are there regions of this volume where the charge density is constant? So are there regions inside this cylinder where this charge density is constant? Okay, along the central axis, it is constant. You're right. Rho is constant. Rho is 0. What else? At the endings. At these points. Yeah, they are also constant because they are at the same distance. Rho is constant. What else? You see, what does charge density depend on? It depends only on rho. So what are the regions for which rho is a constant? No. On a circle, it's a constant. On a cylinder, it's a constant. On any cylinder, it's a constant. Not necessarily this surface or the other surface. You see, if I imagine such a cylinder, I imagine a cylinder inside my red cylinder. There is this blue cylinder inside. This is that the red dashed line is on the center. On the surface of this blue cylinder, my charge density is constant. Now let me just imagine that this blue cylinder has some thickness. And let's call that thickness, let's say d rho. Now it has a finite volume. What is the volume of that cylinder? Of that blue cylindrical shell? If it is, radius is, let's also call that rho. Or let me call it 2h, and this is dh. What is the volume of that cylindrical shell? Well, 2 pi times 2h. This is the circumference. If I open up that shell, that will become a rectangle with some thickness. This 2 pi times 2 pi times h, sorry, not 2h. 2 pi h is one side of the rectangle. The other side of the rectangle is L. I'm just imagining this blue shell to have the same height as my red cylinder. And this is the area of this rectangle. It has a thickness dh. So this is the total volume of this shell. And on this shell, all the points have the same rho. So the charge density is the same. So the total charge within this volume is just sigma times h. Now imagine this is my blue shell. Its radius is h, this is h, this is h, the radius is h. It has some thickness, dh. So when I open it up, it becomes this rectangle. This is the circumference of my ring, of this ring. The circumference is just 2 pi times the radius. The height of my ring is the same, the height of my cylinder, which is L. Now there's a thickness. And so the volume is area times the thickness. This is the area times the thickness. This is the total volume of my blue shell. If I multiply it by the charge density per unit volume, or the charge per unit volume, which is the charge density, I get the total charge in that cylindrical shell. Agree? No? Well, in fact, what we are doing over here is exactly what we had done when we were evaluating the electric field of an infinite plane. You see, if you imagine there, what we had done is we had this infinite plane. There we imagined it to be made up of very thin concentric rings, larger and larger rings. When we summed up all the rings, it became the infinite plane. Here we are making something very similar. I have this infinitely long cylinder. I am assuming that that infinitely long cylinder is made up of very small cylinder, a larger cylindrical shell, a larger shell, a larger shell, a larger shell. So I'm just summing up all these shells to obtain my cylinder. To obtain the total charge, what I will do is I will calculate the charge of each one of these shells. We had already calculated that. And now if I sum the charges of each one of those shells, that would give me the total charge of my cylinder. That is what I am aiming. Well, that summation is just the integral. Well, the innermost ring, the first ring, has h equal to, remember, h is the radius. What is the radius of the first shell? 0. And the largest shell that makes my red circle is rho. So this is the charge enclosed by my ring. So I had evaluated the Gauss law, the area integral in the Gauss law. Now I know, if I know what sigma is, I can evaluate the charge density. So if I just combine them, E rho times 2 pi rho times L, this should be equal to 1 over epsilon 0 times this integral. That is, 2 pi is a constant, L is a constant. Let me just take them out. 2 pi L. What remains inside is the integral of sigma times h times dh. Now 2 pi L's, they cancel. Now this is the upper limit is rho. So if somebody tells me what is sigma of h, I can just evaluate this integral from 0 to rho and then obtain the electric field on a point inside my wire. Remember, we started by assuming that we are inside the wire. So So what happens if we are outside the wire? We want to calculate the electric field at a point somewhere outside my wire. What will change? Well, let's go back. Let's go over our computations. If we are at a point outside the wire, will the electric field still have this form? This will not change. If that doesn't change, none of the calculations here will change. We will still take a cylindrical Gaussian surface, but this time that surface will be outside the wire, not inside the wire. But the computation here will be exactly the same up to this point. Nothing changes for up to here. This is just the expression of the Gauss law. It doesn't care whether we are inside the wire or outside the wire. That equality will still be the same. The question will still be, what is the total enclosed charge? That will be the only thing that will change. Because if you are outside the wire, no matter at which distance you are, the total charge inside will still be the same. If you have this wire, if you imagine such a Gaussian surface, the charge inside will be the total charge in the cross-section. If you imagine a larger Gaussian surface, still the total charge will be whatever is inside. So the only difference here will be the enclosed charge. This time the limit will not be from 0 to rho, but through all of the cross-section of the wire, it will be from 0 to the radius of the wire itself. That will be the only change. 1 over epsilon 0, 1 over rho, 0 to the radius of the wire, sigma h times dh. This is the magnitude of the electric field at a point outside the wire at a distance rho from the central axis of the wire. And the direction will be always away from the wire.
Why did we write like that? Not the integral.
The integral? Well, let me sketch it. This is my wire. I'm looking at the electric field at some point outside the wire. So I imagine such a Gaussian surface. So this is the Gaussian surface. The red cylinder is the Gaussian surface that I imagine. Of course, the top and the bottom are closed. I need to evaluate the total charge inside. So what do we do? Just like before, we imagine smaller cylinders inside. So I take a cylinder over here with some thickness. It has a thickness dh. A radius h. And for the cylinder, dq is just as before. It is just 2 pi h times L times sigma h times dh. This is the charge of this cylinder. Now, to calculate q enclosed, I have to integrate or sum over the charges of these cylindrical shells. This is 2 pi h L sigma h dh. Now the smallest cylinder has a radius 0. What is the radius of the largest cylinder that has charge in it? That's r. The largest cylinder that has charge has the h is equal to r. So that is why the upper limit is r. Of course, I can imagine cylindrical shells outside my wire, but for those shells, you can think as the charge density is 0. So that's why they don't contribute. Questions? Okay, there was one more problem that we solved using integrals. That was the infinite plane. Again, let's try to solve the problem of the electric field created by an infinite plane using Gauss' law. We have an infinite plane. We have a surface charge density, let's assume it to be uniform this time, of sigma. So how can we apply the Gauss law here? Well, this is essentially the last type of problems where we can apply the Gauss law to determine the electric field. No, it's infinite plane. This goes up to infinity in all directions. Or if you look at it from the side, this is how it will look like. Just imagine this plane infinitely long. If you just look at it from the side, it will be just a straight line. Well, the first thing, what is the electric field? What do we know? What can we say about the electric field? Assuming we don't know the solution. Points out, it will, why do you say that it points outward? Yeah, it will be pointing outward, but why? What are your arguments? Can it be like this, an electric field line? Why not? Well, you can say that as your friend pointed out. For example, if you take a point over here, there will be, for every very small patch over here, there will be a symmetrical patch over there. For every patch over here, there will be a symmetrical patch over here. They will both create electric fields in these directions of equal magnitude. When you sum them up, the total electric field will be vertically upward. That is one argument you can use. Since it is infinitely long, whatever patch you imagine, there's a symmetrical patch on the other side. So that tells you that it is vertically upward. Let's call that direction the z-axis. Let me call this one x, this one y. Well, or you can say that the electric field line cannot be tilted either in this towards left or towards right. You can just imagine a mirror. If you put a mirror over here, an electric line that is tilted in this direction, its image will be tilted on the other direction. So the electric field lines change through such a mirror. But this mirror, the image in this mirror of the charge distribution itself will be the same. If the charge distribution doesn't change under the reflection of the mirror, the electric field also cannot change. So this is eliminated. This cannot be. It cannot be tilted to one side. It has to be vertically up. It has to start from the plane, from the positive charge, and the only possibility is that it has to be pointed upward. Of course, it has to be pointed upward on the top and downward on the bottom. At this point, it should be pointed upward. At this point, it should be pointed downward. What about the electric field of this point and this point? At this point and this point, they are of the same distance from the plane. Just shift it. What can you say about their magnitudes? We already determined their direction. It has to be in the z direction, either upward or downward. What about from this, if you look at this point and this point, what can you say about their electric fields? They should be equal. Because if you imagine yourself sitting over here, or if you imagine yourself sitting over here, you will see exactly the same thing. So the electric field should be the same. But this point and this point, they have different x and y values. So the electric field should not change as you change the x and the y values. It tells you that the magnitude of the electric field can only depend on z. It cannot depend on x or y. It can depend, if at all, on z. And secondly, it should be along the z direction. It should be either pointing upward. It's always pointing away from the plane. That we know. Now, what kind of a Gauss surface should we choose? So we should choose some surfaces over which the magnitude is constant. What are those surfaces? Well, if you imagine such a circle, the electric field is not constant. Because you see, if you imagine such a circle, this point on the circle has the z value this much. If you go here, it has the z value this much. So over such a circle, z changes. So that cannot be my surface. Well, so if you imagine such a circle, then z is constant. So over such a circle, the magnitude is constant. But as your friend pointed out, well, z is equal to constant is just a horizontal plane. So any horizontal plane, on any horizontal plane, the magnitude of the electric field will be constant. But you cannot form a closed surface from a horizontal plane. We have to imagine some closed surface. Okay, we can take part of a horizontal plane some horizontal area. But we have to somehow close it. Okay, so we can now look at the direction. Well, the electric field is pointing upward. So we have to add, to this area, we have to add some other areas whose area vector is horizontal so that it is perpendicular to the vertical electric field. So what are those surfaces? The area vector should be horizontal. But area vector is always perpendicular to the area. Any of these areas, they have an area vector which is horizontal. So I have this area. To that area, I can add such areas. But that is a cylinder, a vertical cylinder. Well, not necessarily a circular cylinder. It doesn't have to be. But I can just close it by such areas. Now, there was one thing we didn't mention. Let's look at this point. Okay, we had this point already. Now, let's look at the opposite point on the other side. So if this is H, this is also H. What can you say about the magnitude of the electric field at this point and the magnitude of the electric field at that point? It should be the same. So basically, if you take these small patches, this one will create an electric field in this direction. This one will create an electric field in this direction. When you sum them up, you will get an electric field pointing vertically downward. But this image over here and that image over here, they are identical images. It's just twisted, pointing downward. So if you just sum all the contributions, well, whatever they contribute to this point, they will contribute exactly the same on this point. So, okay, so we are now closing this closed surface, but I would rather use a Gaussian surface over which either the electric field magnitude is constant or the electric field vector is perpendicular to the area vector. On this surface, okay, the electric field magnitude is constant. On the side surfaces, the electric field vector is perpendicular to the area vector. But now I have to close this surface by another area over which the magnitude of the electric field is constant. That will be essentially the same area on the other side. Let's say if this is L, just below, I take this L, I just close it with the same surface. I have a straight cylinder whose cross-section is not circle, but nevertheless it's a cylindrical object. Well, this top area and the bottom area, their shape is arbitrary. I don't really care. It won't be important for me. Okay, now we have chosen our Gaussian surface. Now let's evaluate E dot dA. Well, I will divide it into three parts: the top area, the bottom area, and the side. This will be E dot dA over the top plus E dot dA over the bottom plus E dot dA over the side. Over the side, what is the direction of the dA vector? Horizontal, somewhere. I mean, as you cross the side, it points everywhere, but it will be horizontal. It doesn't point up or down. It's always horizontal. The electric field is up on these parts or down on these parts. But in both cases, the electric field and the area vector, they are perpendicular to each other. So the scalar product of two perpendicular vectors is always 0. So this is 0. I only get contributions from E dot dA from the top and E dot dA from the bottom. Well, on the top, E dot dA is the product of the magnitudes. The magnitude of the electric field is EL on the top. The magnitude of dA, well, they are both pointing in the same direction. They are both pointing in the same direction. So the angle between the two is 0. So this is it. Cosine 0 is 1. On the bottom, the magnitude is again E dot L, E evaluated at a distance L, because we said that the magnitude on the bottom is the same as the magnitude on the top because of this. So it's exactly the same magnitude, multiplied by dA. At the bottom, the A vector is pointing downward. The electric field is pointing downward. So the angle between them is 0. So cosine 0 is 1. So this is it. Well, EL is just a constant. I can take it out. What remains is the integral of dA. Well, the cross-sectional area, we had chosen it to be A. The shape is not important. The total area is A. So I have A from here plus EL times A from the second integral. This is E dot dA integral. Now I use the Gauss law. Gauss law tells me that this integral E dot dA should be always equal to the enclosed charge divided by epsilon 0. This is where I write the Gauss law. Well, let's look at the total enclosed charge. Well, here this is a surface. It has a surface charge density sigma. It has a surface charge density sigma, which tells me that if you take any surface, any area on this surface, well, this is an area on my surface. This much of my surface is inside my cylinder, and that has an area A. This part also has an area A. So the total charge here is just sigma times A. Sigma is the charge per area. I have a total area A inside my cylinder. So if I multiply the charge per area by the area, I get the total charge. So this is the total charge inside my cylinder. So 2A times EL this is equal to sigma times A over epsilon 0. A cancels. So the magnitude of the electric field at a distance L is just sigma over 2 epsilon 0. Any questions? Yes. You can ask questions now. Okay, see you on Monday.